So at the conclusion of my last video, said we were going to talk about the LEDs using this project. So this is a string of LEDs. It contains 300 LEDs. Each LED is RGB, and each LED is intelligent. I say intelligent loosely. We'll get into why they're not super intelligent, but they are addressable. This particular strip works on 5 volts. There are some of these that work on 12. The ones that I've seen that work on 12 typically have a voltage regulator on the back, and they're not ideal because it's harder to mount them on a flat surface, and and also from the variants that I've seen, you cannot cut them at any intersection of LED. This strip you can cut anywhere. Anywhere you see these little copper pads, you can cut, which is ideal for a project like a spectrum analyzer, because you want to be able to make each column your desired height. Alright, so basically this strip works on 3 wires. Okay, there is a 5-volt line, a ground, and a data line. You can see that in this plug over here is 3 wires. And these 2 wires here are just auxiliary power wires. You don't have to use them. Also notice that on in the front of each LED there's a little triangle, and that's the flow. That's the direction that data flows from the data wire, this green wire. So you can only go in one direction with this. You can't power it from the other side and come this way. It won't work. And we'll go into why that is the case. These LEDs are susceptible to overvoltage. They're susceptible to reverse polarity. Each one of these LEDs has some electronics inside each die, and if you overvolt or put reverse polarity on this strip, you're probably going to damage the electronics that is inside. And if an LED is damaged, it cannot pass data to the next LED. So if you have a string of LEDs and this LED goes bad, well, all the LEDs after it will not receive communication. And that is a limitation of this particular standard. This is known as a WS218B LED strip. Alright, so now let's look at how these things work. So what we have here is a representation of the LED strip. Here is your 5-volt rail, and this rail runs throughout the entire strip. Here is the ground rail that runs along the entire strip. The third wire, the data rail, also runs along the entire strip, but is interrupted by each LED. Now, this is a physical representation of what's happening inside the LED electronically. This is not how it actually happens, but I'm just trying to, simplify these concepts into, I guess, easy to digest language. Okay, at the end of this data line here, you would have a computing device like an Arduino or a computer that could communicate with the LEDs serially. Okay, the data that you pass to the LEDs is typically handled by a library that has been written already, or you can opt to send the data to the LEDs by means of your own code. So let's walk through what would happen with these three LEDs. Okay, I'm going to command my Arduino to begin sending data to the LEDs, and wait, let's go back a little bit. Notice that the only LED that can receive data right now is the first LED, because there is a little drawbridge here that prevents data to get to LED 2 and 3. And also notice I've kind of drawn in this little hole here, which is kind of like a trap door. And let's see what happens when I start streaming data to the LEDs. This data is going to come in a burst, a very rapid succession of packages. Each LED can accept a 24-bit package. Now I'm not going to draw 24 ones and zeros here. I'm just going to put a small a little bit of numbers there just to represent that package, just so you get an idea of what's happening. So I'm going to start streaming my data now. So the first 24-bit package has traveled down the line, and it's fallen in this little trap door here. But that's great for the next package because this little 24-bit package has pulled down on this little lever and pulled that trap door shut, giving the next package the ability to get to RGB LED 2. Let's see what that looks like. So here comes the rest of the data. Here's the next 24-bit package that has made it past this LED and is now on its way to the second LED. And the third 24-bit package is also en route. Okay, you can see that the second 24-bit package fell into the trap and pulled this door shut, and it made way for the rest of the packages to clearly cross to LED number 3. So this package is going to fall in this hole, pull this door closed, and so on and so on. This is happening hundreds of thousands of times per second. I mean, faster than you can imagine. And it has to be able to do this fast. This entire thing has to look like, a moving picture to us. The refresh rate has to be pretty high in order to fool the human eye. So these ones and zeros are traveling at an astounding rate. Okay, so now what happens after the last package is sent? Well, either your code or the library will know that the last packages went out, and it's going to insert a little break. It's going to take a timeout. That's going to insert a pause. And typically that pause is going to be greater than 9 milliseconds, but I think the specs for these LEDs may call for up to 50 microseconds. So each one of these LEDs is programmed to listen for that silence, and when it hears no data coming through for that specified amount of time, all of these packages that were sitting here holding these doors closed are dumped. So this package will fall off, this package will fall off, and all the doors will now resume to this position. And then you start the whole process over again. So every time that you send this blast of information through, you're potentially changing the color and intensity of each one of these LEDs. And you're doing this in rapid succession. I hope that covers it all, and I hope that was clear enough and simple enough. It's a lot easier to troubleshoot these devices once you understand how they work, and now you can even watch the movement of this on an oscilloscope. You can watch this data on an oscilloscope. Also, this kind of will demonstrate how if one of these LEDs, like say this LED in the middle, got destroyed because you overvolted it or you put reverse polarity on the LED, I mean, you essentially break this door. It just kind of explodes internally, and now you have a crater here where data cannot pass over to the next LED. So in this regard, the LEDs, they're really not intelligent, right? Like this LED doesn't really know what number it is in the line of LEDs. We're just hoping that the host that's sending this data knows how many LEDs are there and is packaging the data packets in the proper order and for the proper LED, so that we get a fluid light show. And this will also kind of demonstrate, while let's say we only had 3 LEDs in this setup. If I wanted to only light one of the LEDs, I would still have to send something to the first LED. It may just be null data, like blank data, maybe all zeros, but I would still have to send a 24-bit package to this LED. Or else there would be no way for me to send the second package to the second LED. So if you only wanted to light one LED, you have to kind of plan accordingly, and you have to send null information to all the LEDs preceding that one. And you probably, in best practice, have to send null information to all the ones after it. I guess you could just insert a pause after this, if a pause of 50 microseconds, and start the process over. But I think it probably is best to write null information to any LED you don't want on, and just send the data you do want. All right, let's move on to the next part. Okay, so now that we've kind of gone over how these LEDs work, let's talk about how I wire them for the spectrum analyzer. Remember, I said these LEDs can be cut at any point where you see these little oval pads. So if you cut on that dotted line there, it gives you half of that pad that remains behind that you can solder to. You can solder little wires onto that. And basically this is 3 bands of many, but this is how it would start. So the first band, let's call it band 0, will receive the power, right? So this one will have 5 volts here. And remember, these LEDs are super sensitive. 5 volts is the maximum. Don't try to push 6 volts, 7.5 to them, because you're gonna get some very unhappy LEDs. These LEDs, they're not gonna blow up in smoke or like like other components will. They're just going to fail, and you're not going to know why. You're just going to sit there scratching your head wondering what happened. So you have to be very careful when you're working with them. The second wire here, this is going to be ground. We can say like this, GND. And the wire in the middle, this is going to be data. And this data line is coming from an Arduino. Okay, and so when the Arduino is talking to all these LEDs, it is going to talk with this LED first, then this one, then this one, then this one, then this one. However, the Arduino does not know that I've cut these segments up. So we have to provide a way to get this signal back down to the next segment. So basically, if you looked at my very first video, you saw the strips taped onto a white board, and then on the back of the board I had a bunch of jumper wires. Okay, so it's going to look something like that. It's going to come into this one first. It's going to address each one of these LEDs, and then it's just going to move down this line and move to the next LED, and then we're going to do that over and over for all 14 bands. Okay. Remember, this data line can only work in one direction. You can't inject the data here or here. You're going to end up with bizarre results if you attempt to do that. The 5 volts and ground, sometimes you have to feed that in at more than one spot. It all depends on how many LEDs you have in your string. Okay, just imagine that there are losses there's losses and voltage drop that occur along the string. Number one, this 5 volts is traveling through pretty thin foil, and there is a voltage drop with that thin conductor, but then there's also losses from driving each LED. So by the time you get to the end of a long string, you could have enough voltage drop that would cause some LEDs to start acting erratic, because remember I said these LEDs require 5 volts, and if you had a very long string of LEDs, say 1,000 of them, you could potentially end up with less than 4 volts at the end of the string. And those little drivers, they don't like to be undervolted. Also, the colors may start to appear different at the end of the string, because each of the LEDs is being driven at a different intensity, because it doesn't have that solid 5 volts there. So with the 5 volts and ground wires, you can feed it here at the beginning, and you could use some nice solid wires and jumper that all the way back to the end of the string up here, and that would feed the 5 volts and ground from both sides. Remember, the LEDs don't care which way the voltage is coming from, as long as it has a stable voltage supply. Now, with my particular setup, I didn't have to do all that. I was only running 294 LEDs. They were all in close proximity, and I didn't notice any strange artifacts from not powering the LED string from both sides. So for me, it just made the layout a little easier and one less thing to worry about. But if you're using wire that is not copper, might be tinned or something like that, or I would highly recommend that you use high quality wires for these interconnects. All right, because the better this wire is, the less voltage drop you're going to have. Now you can put thicker wire here, but then it becomes a little hard to solder onto these little pads. Okay. So you kind of have to choose your poison there. What I used was a stranded full copper Cat5. Okay. You really don't want to use solid Cat5 here because they tend to want to pull on these little pads when you're trying to position everything, and you could end up ripping one of these little pads right off. And once you do that, you pretty much have to cut that LED off and throw it away. So the stranded Cat5 wire, which you typically would see in 6-foot jumpers for patch panels and stuff like that. You can kind of tell. If you don't want to cut the wire open, if you take a Cat5 wire and you kind of bend it at a 90-degree angle, if it stays at that 90-degree angle, it's probably solid conductor. The stranded stuff is way more pliable, and it doesn't have that same kind of memory effect, and that's why I like using it with this project, because when I solder these 3 connections here and kind of drape the wire down to the necks, I don't have to worry about yanking on these little tabs too much. All right, so that pretty much covers that. Let's go on and talk about something else. All right, so I think this might be my last revision on this project. I've spent a lot of time on this, and I think I got it to the point now where I'm happy. So let's talk about this new revision. In my previous video, my board was half the size of this, but then I put a little bit more thought into it and figured, if somebody was gonna say buy one of these boards for me, they wouldn't necessarily have a non-standard Arduino Mega on hand, right? You have to go ahead and order one, and it takes forever to come. But with this board layout, it will work with an off-the-shelf Arduino Mega 2560. It's the same footprint, and once the headers are soldered in here, it'll sit right on top. In fact, here it is right now, seated on a Arduino Mega. So there's your Arduino, and I don't have every header. Filled in. It's not required. I'm leaving a lot of this stuff blank for users to use the Arduino for other things. I did install tall headers in certain positions to give end users the opportunity to add, say, a button for some special feature that they wanted to write code for. Maybe they wanted to use a button to put the entire thing to sleep, or maybe use a button to change the color palette that the spectrum analyzer is displaying. Some of the other improvements I made with the Specky-Board, I used proper level translation between some of the components on this side and this side. For example, this little chip here works on 3.3 volts, while this one over here works on 5. And while they could talk to each other, there is a chance that something could be missed because the voltages are really not compliant. So what I've used is some buffers to kind of raise the voltage up so that when they talk to each other, they're happy. And pretty much the clocking has remained the same. There's a crystal on here which is going to give rock solid clock signal to the frequency slicers, and there's not going to be any drift or anything like that, or you won't have to worry about stray capacitance or clocks drifting because of the way the board is mounted or anything like that. It's going to always put out the specified frequency. I also added a pass-through through this header up here for a gain potentiometer, because you know, sometimes you may listen to music selections that are recorded quiet, right? And so you might have to boost the gain on the spectrum analyzer to get kind of a full deflection. Or you may be listening to something very loud, like heavy metal track or something like that, and you might have to bring the gain down a little bit, because if not, the entire thing would just be pegged at the top because the passages are so loud. So it gives a little bit more flexibility and allows you to tailor this to the type of music you listen to. Also, different output devices may put out different levels depending on who the manufacturer is. So adding the gain feature makes it compatible with more consumer electronic gear. It should be noted that this thing will only interface with line level outputs on consumer electronics, like a preamp or a receiver. When I say line level, I'm talking about like a preamp output or a tape loop output. So you have to know that you cannot feed speaker level inputs into the Specky-Board. I mean, it's not designed to handle that amount of power, and you will certainly destroy the Specky-Board, and you may even destroy an amp. So it should be noted that this is only used with line level equipment. Let's see, what else did I change on this? I've provided 5 volts and some ground points over here for so you can utilize the power that comes off this board for buttons or a buzzer or something like that. Let's see what else. All right, power here. Yeah, this is pretty important. So when I put together a kit for this, I include like a buck inverter, and what that buck inverter does is it'll raise 5 volts to some predetermined voltage. In my case, I'm raising 5 volts to 7.5 to 8 volts. So why do we need to do that? Well, it's very simple. I'm trying to utilize one power source for everything, including the LED strip. Right? So we know that the LED strip works with 5 volts. All right? The Arduino, the core inside the Arduino, requires 5 volts. And the Specky-Board requires 5 volts and 3.3 volts. Now, if you are using the USB port to power this, well, the Arduino is assuming that you are feeding it 5 volts, and the 5 volts is coming from a regulated source. All right, so it's not too concerned about regulation at that point. And if you're using this barrel connector over here, this barrel connector is certainly going through this 5 volt regulator right here. And this 5 volt regulator will power the entire Arduino. But here's the rub with this regulator. This regulator requires more than 5 volts to regulate. So if I were feeding 5 volts into this barrel connector, it would go to this regulator, but this regulator would not be functioning. It would just kind of be coasting through it. In order for that regulator to turn on and actually regulate anything, it has to receive a voltage that is 1.5 volts higher than its output. So this regulator, it has losses in it, and it has circuitry in there. And you can't expect to feed in 5 volts and get out regulated 5 volts. There is some overhead that it uses. It consumes some of that power. So if you feed it 8 volts, it will give you a rock solid 5 volt output. If you feed it 5 volts, the results are not guaranteed. So that means you can have 5 volts coming into this barrel connector, and you don't know, and you're not sure that it's really regulated, and so that unregulated voltage gets into your Arduino circuitry and now causes the Arduino to act erratic. I'll give you a pretty good scenario of what could happen here. Let's say we were running this whole thing off of the same 5 volt power supply. These LEDs can draw instantaneously a lot of current, can cause some voltage sag. If we were sharing the same 5 volt power supply for all of this, this barrel connector could see that voltage sag, and that voltage sag is going to get passed along to all the circuitry on this, including the Specky-Board, and you can end up with unintended results. So how do we get around that? Well, we provide a single 5 volt power source, and let's just say this camera was my power source. Right? This power source provides 5 volts, and that is everything that this LED strip wants or desires. I mean, a nice solid 5 volts. Doesn't necessarily have to be tightly regulated. But, most wall wart type, not wall wart, but I mean most little brick power supplies are regulated. So the 5 volts that this guy requires, it's there. It's got a nice fat wires that can handle the current, and it will take whatever it needs. Then in between the Arduino and this power supply, I insert a little buck inverter that takes 5 volts and converts it to 8 volts. And so now when I feed 8 volts into this barrel connector, that 5 volt regulator inside the Arduino now becomes satisfied and will happily regulate that 8 volts back down to 5. Even if there is some little sag in voltage over here, the buck inverter is going to handle that. It's going to always try to put out 8 volts, no matter what this 5 volt supply is doing. And this 5 volt regulator on the Arduino, as long as it's getting more than 7.5 volts, it is going to deliver a constant 5 volts for the rest of the circuitry on the Arduino and the Specky-Board. So we went from this on the drawing board to this. All right. Note that I build all of these boards by hand. Okay. This is kind of a niche project, and I don't have thousands of people asking me for this. So, the cost involved with having automation and robotics build one of these is kind of high, right? So I have to build each one of these by hand. And so a great amount of the cost in building one of these is the vast amount of time I have to spend manually placing each one of these components and soldering them. It may be hard to see here, but here's a tip of a pen, right? This is a standard pen, and that is one of the ICs that I have to solder. The tip of this pen is longer than the IC. So you can imagine what it's like trying to solder some of these components. Everything on here is surface mount. Nothing is through hole. And I have to use a stereo microscope to manually examine my solder connections after everything is said and done. And I use specialized gear to do the soldering, and just standard techniques that anybody would use with these small components. There's some special techniques that are used with hot air workstations and preheating this PCB in order to make things flow easy. But it's not as easy as one would think. Now, people ask, well, why don't you just do this in a through-hole version? Well, some of these components are not available in through-hole versions. Like this timing IC is not. Capacitors and resistors, sure, you can get those in through-hole versions. And you can even get these frequency slicers in different formats. But the reality is that a properly designed board with surface mount components is going to perform better than an equivalent board that has through-hole components, because of the way the ground planes are laid out, and there's going to be less susceptibility to noise when you're using small surface mount components like this. If you take a good look at this board, you're going to see that they're surrounded by nice ground planes, and the possibilities of crosstalk between some of these very high frequency lines is minimized because of the way the traces are laid out. So it took some time to lay this out, and I know it's been a long time since I did the last video, but the reality is you want to try to do this the first time. You don't want to have to do this over and over and over again. It takes a long time to get one of these printed. They get sent off to China, and by the time it comes back, weeks have passed. So it's better to try to get it right the first time. So, let's look at the control box that I put together for my system. Okay, so you've already seen my spectrum analyzer and the housing that I put together for it. Some of the construction for that is shown at the end of video number 2. And so this is the control unit for that. There are no electronics other than the LEDs in that frame that I have hanging on the wall. I just have a thin umbilical wire coming down the wall and feeding into this box. It's an aluminum enclosure. Inside here is an Arduino, a Specky-Board, and a buck inverter, and that's it. Here's the back of it. I have RCA connectors for the signal in. This is left and right. This signal is summed internally and is summed to a mono signal internally, and that is fed to feed all 14 bands. This lower connector is my power in. That is coming from my 5-volt power supply, and this is feeding the umbilical to the frame that's on the wall. On the bottom I have some little rubber feet, and on the front I have this very handsome copycat of a Mark Levinson knob, which I really fell in love with because I love Mark Levinson. So it's a very clean design. It sits on my desk like that, and I can control the gain right there from my seated position. I was going to put an LED on it, but then I thought about it and I was like, man, I got enough LEDs hanging on the wall. I don't need another one. So I kind of left it muted and quiet. It is pretty stealthy, I think. And I think it looks good like that. Got fingerprints all over it, but I hope you like it. I'm certainly happy with it, and this thing doesn't produce any heat or anything like that. Even if it did produce heat, this is black aluminum, so it would dissipate heat pretty easily. But the components inside, they produce no heat, so I'm not concerned. Also, it doesn't draw much energy at all, so I don't really have a power switch on it. I may add one on the back here somewhere, or maybe a small push button or something. But for the time being, I just leave it powered on. It doesn't really consume that much energy when there's no LEDs being driven. Okay, well, there you go. I hope you like it. So some people asked me about the construction of my analyzer, and I kind of went over it briefly in my previous video, but let's talk about what I did. So this is one of the jewel elements that I created, and I bought this acrylic stock in 5-foot lengths, and they came shipped to my house in a tube. It wasn't that expensive, but what I did was I made a jig out of a piece of wood, and then I used that jig with my bandsaw so that I could create a bunch of these, 300 of these, without having to measure over and over again. I just would drop the acrylic in the jig and cut, and then push it out and do the next one and cut, and just do that over and over until I had 300 of these. I didn't do anything to finish the end of these. It kind of looks frosted, which is ideal for me. I mean, if it was clear like this, you'd be able to see the LED. But just the action, or just the act of cutting it with the bandsaw, kind of gave it a nice frosted finish. I would imagine if I was using a fine tooth bandsaw, so it didn't really dig a lot of grooves into the face of this, and it left it really smooth on both sides. It still can transmit light from the LED with no problem, but as you can see, if I lay this on top of the LED, you can't really see the LED anymore. So I mean, you can get this acrylic in square form, you can get it in rectangular form, you can even get it in round. Now I had to cut the panel to insert these on my CNC machine. Most people won't have a CNC machine available. However, you can get round stock and drill round holes into a piece of plywood or something like that, and you can insert these in there. You just have to plan it out and space the holes out accordingly. So let me give you an idea. I did a couple of trial runs with this stuff before I did the final board. And so this is one of the boards that I used for a trial run. Actually, you know what? This is not even going to fit in here because on my initial runs, this hole was just a little undersized. But basically, you can get the idea of what happens here. I cut these squares out, I push this through here, Let me see if I have another hole here on this board. Okay, here's one on this side that will work. So here's one right here that works. All right. So I pushed a jewel in there like that, and then on the back side, right there, you can see how over here I made some boo-boos when I was testing, but you know that's expected. On the back side here, I just took hot glue and went around each jewel element. And you know, I used a pretty beefy glue gun, right? You know, I used like an industrial glue gun that I was able to borrow from my job with really long glue sticks, and I just kind of poured it in around each one, and it held them. It held them really good. You know, they weren't going to come back out for sure. But you could do the same thing like that, like I'm doing here, except you know, use round stock and drill round holes. And you just got to make sure that you get the right bit for the size stock you're using, because you don't want it to fit loose. And you can do the same thing, just glue around it afterwards. I think it would look great with round stock. Yeah, I think it looked pretty retro, to be honest. Anyway, so 300 of those took me a couple of hours to complete, because as you're cutting through this stuff, it tends to form a little bit of melted junk over here. All you got to do is wait for it to cool and then just flick it off with your fingernail and it comes off. You didn't really have to do any sanding to any of these. I was just able to clean all the edges off with my fingernail once the acrylic cooled after cutting. So just one of many ideas. I'm hoping to see other people's implementation of this and see what kind of ideas they come up with. All right, so I got the music muted now. I just wanted to point out that this frame that I built out of pine wood, basically, I have it channeled over here to receive real glass, which keeps dust out. Also, the entire thing is being fed from this very thin 4-wire conductor. I'm only using 3 of the wires, but you know, this is high quality cable. This is the type of wire that would be used in like alarm systems and fire control systems. So you know, high quality copper. So there's not much voltage drop, and it's really not traveling far. The little control box for this entire thing is sitting right on the desk below. So from up here you can see the analyzer, but down here is where the control box is. So it's really, that little umbilical is not traveling very far. I have it connected to, I'm quite proud of my vintage rack of gear. This kind of stuff here is the reason why it took me so long to even make this third video, because I spent a lot of time restoring vintage gear, like this amplifier down here. That's a Mark Levinson. But I did a full restoration on that guy. But go back to that. You can see that you don't really need a large umbilical to feed the frame. I mean, I wish I would have had some white wire. I probably can get my hands on some, but that's what I had, and it doesn't look bad. The frame is gray and that wire is kind of greenish gray, so it doesn't look too bad.